I'm John Price. I'm a retired physician, and I got interested in the climate problem a while ago, and then I realized that this was going to be a very big issue for my young grandkids. They're way too young to know anything about it now, but the way it looks, if we don't do something pretty soon, then they'll wake up to the problem and find that we left it too late. So that was what made me decide to try to do something about it. I'll just introduce you to a few of them now. Here they are down at the beach last summer. Now, if you're a grandparent, you'll know just what it's like to look at them and wonder about the future. What will it be like when they're our age and maybe thinking the same things about their own grandkids? And there's something very, very ugly about the idea that they might have to wear the consequences of something that we should have prevented. In 1945, after the atomic explosions in Japan, scientists began to realize that their discovery had brought vast implications for future generations. Sometimes they saw knowledge brings responsibility. Well, it's like that now. Scientists have been trying to tell us for years that a huge ecological problem is on the way. It would be visited on these little kids, people of the future. And if we're to avert it, we have to do it now. Now, you've been entitled to ask, well, can we really have clear and certain knowledge about the future? Isn't it all guesswork? Well, the answer is yes, we can. And no, it isn't guesswork at all. This is my grandfather, as he was just over 100 years ago, just before he emigrated to Australia. Now, if anyone had suggested to him that before he died he would see men walk on the moon, he would have thought it absurd. This is the kind of foreknowledge that we can't expect. But we can observe and measure patterns in the events all around us, trends. And when they're properly understood, they're as clear as signposts. I'm going to show you 3 of them. Here's the first. This graph shows what's happened to the human population over 8,000 years. Obviously, something happened about 3,000-4,000 years back. That was when we learned how to establish empires and live in bigger and bigger cities. That sort of upward trend that you saw turned into something quite different about 250 years ago. 1800, we reached 1 billion. And then every billion that's come since has come faster and faster and faster. When grandfather came to Australia in 1910, there were 1.6 billion people in the world. A century later, when my second grandson came, it was 6.5. Now, just imagine you had a farm and I was studying the population of rabbits on the farm and I showed you this graph. You'd know right away there was a problem. And the name of the problem is a plague. Everything eats, and food supply is one of the things that limits population, so this can't go on forever. Of course, humans have a great many more needs than rabbits, and our impact on our environment is correspondingly greater. But just like rabbits, we can gobble up the resources that really belong to our descendants. Now, by 2050, the experts tell us there should be around 9 billion people on Earth. That's an increase of 50% over what we have now. And most experts are very concerned about this. It would be different, they say, if all along we've been taking account of what we used up and what we could replace, but we haven't been. That's apparently not something that humans have ever done in history before. This is a very complicated subject. The problem has many consequences, but I just want to show you one of them now. This is the island of Borneo. It's the 3rd biggest island in the world. 50 years ago, as you can see, it was covered in a tropical forest. Today, there's not much of that left, and what is left will probably only last a few more years. Now, it's no coincidence that that happened in the same 50 years that the human population doubled. Adding 3 billion people, large mammals, to an ecological system is a pretty big deal. That's what it used to look like in Borneo, and that's what it looks like now, at least a lot of it. That's a giant palm oil plantation. All the world's tropical forests are being treated much the same way. That's what's left of them. About 100,000 acres of tropical forest disappears every day. Some of it logged, but an awful lot of it just goes up in smoke. Bad news exactly like this could be given about many other problems with human impacts. The depletion of fish in the ocean, for example, the loss of topsoil on cultivated lands, the expansion of deserts, the shortages of fresh water, and many more. These are all stories about the loss of resources that rightly belong to our descendants. Just take a look now at the bottom right corner of this again. Whatever happened there is the key to our story, and I'm going to come back to it soon, but for now, take a look at another well-measured trend. This chart shows the mean temperature of the Earth's surface for 160 years. Why 160 years? Well, that's about as long as there have been enough weather stations around to make these measurements. The 3 colours belong to the world's 3 main global temperature monitoring centres: the Goddard Institute in New York, National Climate Data Centre in Colorado, and the Hadley Centre in the UK. You can see that they pretty much agree. The thing is that from here to here, in 1 century, the mean temperature of the world has gone up 0.8 degrees. Now, I tell you now that that's a pretty big rise. It's fast and it's large. This is another way to show the same thing. Here the individual years are ranked, with the hottest ones on the left and the coldest on the right. The latest 50 are there in the middle, so you can see them clearly. There are 19 following 1990, and of those, 15 of them occupy all of the top 15 places. The others are 19, 21, 23, and 30. Of all the years since 1970, all but 2 of them are in the top 30 places. Here's the 20th century warming in a longer context. Temperatures before 1850 have to be recovered by scientists from various clues buried under the sea, in ice, in all sorts of places. And although these techniques aren't as accurate as thermometers, there are quite enough of them to establish a trend. You can see the trend there. 20th century warming is severe, sudden, and unique. Where does all the heat go? We know it doesn't stay in the atmosphere. That gets hot and cold all the time. No, the heat is in the ocean. The ocean is by far the biggest heat reservoir on Earth, and people have been measuring the ocean heat content for some years now, and there it is. Another steadily rising trend. Now, I want to say something more about the climate history of Earth later on, but for now, just take a look at this. Another trend unique to our time. This is a measurement record made at an observatory on the side of a mountain on Hawaii, specially built for the purpose. The man who put it there is Charles Keeling. What he wanted to do was to pin down exactly as he could what was happening to the CO2 in the air. And it's thanks to him and his successors that we know beyond a shadow of a doubt that this gas has been accumulating in the atmosphere at least since he started measuring in 1958. And that when it began, its concentration was 315 parts per million, and now it's 390. Look carefully at the graph again. That sawtooth pattern is something Keeling discovered. And within a couple of years he'd figured out the reason. The great northern forests of the world draw down carbon dioxide during the summer when they're growing and release it again in the winter. And after a few years he found that the mean had risen about 0.7 parts per million, and it kept doing that year after year. But look again at the red trend line in the middle. It's not a kind of rough straight line, it's actually a curve. And the increment that Keeling measured back then has tripled. It's now a bit more than 2 parts per million and rising. CO2 is measured in many places in the world now. Here are 4 of them, way up in the high Arctic in Alaska, Hawaii, Samoa in the middle of the Pacific, and the South Pole. You can see that the 2 southern hemisphere ones don't have much of that sawtooth pattern, but they share the rising trend just the same. Now, these 3 clear signposts to the future, the human population explosion, the century of greenhouse warming, and the rising atmospheric content of greenhouse gases, are not really separate problems at all, but very closely connected. Look at the population graph once again. What happened in the middle of the 18th century was a convergence of several things. First of all, living standards were rising, not for everybody, but for enough. The second thing was that the colonization of America began in earnest. Millions of Europeans went to find an enormous ecological opportunity. And then there was the Industrial Revolution, an enormous change in the way we live and produce. And part of that was triggered by simply running out of wood for industrial use and switching to coal. See, what we're doing when we burn fossil fuel is releasing solar energy which has long been buried under the ground. All the fossil fuels are the residues of organisms that lived on the Earth typically hundreds of millions of years ago. When we pump them up and dig them up, we combine them with atmospheric oxygen, we capture the energy, and we release the gaseous products of combustion into the air. Now it so happens that these are invisible. They don't smell, we can't see them. And so we've been releasing enormous quantities into the atmosphere for a long, long time, not realizing until very lately that it was doing any harm. Most of the product of combustion is carbon dioxide. And everybody knows by now that carbon dioxide is a problem. But why? I'll just show you now. CO2 is just one of a number of gases that have the same property. They can trap Earth's radiation. This is roughly how it works. Sunlight passes straight through the air. These gases have no effect on that because sun rays have a different wavelength. But the Earth is warm rather than hot like the sun, and it radiates at infrared wavelengths, and those rays smack into greenhouse gas molecules in the air, which become energized and eventually re-radiate rays of their own. And in this fashion, infrared is trapped in the atmosphere. Eventually some rays reach the top and are lost into space. But in the meantime, the heated atmosphere down below is what keeps the Earth warm. It's just the same as adding a blanket. The strength of the effect is determined by the amount of gas in the air, and the concentration on Earth has been going up very steadily. In fact, this rate of increase is unprecedented. No student of climate history has ever discovered anything comparable to what we're doing. Just to give you an idea of how much and how fast this has been changing, here are a couple of graphs from the IPCC 2007 synthesis report. This shows you what's happened to the CO2 over 10,000 years. Now you might wonder how we could know how much CO2 was in the air 10,000 years ago. Well, it turns out there are actual air samples from that age stuck in the ice in Greenland and Antarctica, and they can be recovered in ice cores and measured directly. These are precise measurements, there's no problem with that. But look how steep and rapid the modern rise has been, from 280 parts per million in 1800 to 390 today. This shows where CO2 has been for the last 400,000 years. This is taken from an Antarctic ice core drilled near the Russian base of Vostok. Turns out that modern rise is unique not just in hundreds of thousands of years, but in tens of millions. This is methane, another powerful greenhouse gas, not as prevalent as CO2, but sharply affected by human activity. In fact, in percentage terms, methane has risen much more than CO2. And this is nitrous oxide, a greenhouse gas produced particularly by modern industrial activity and the use of nitrogenous fertilizer. So the situation we've created for our grandkids is one of a crowded world and a hot future. Now, if you've been interested in this issue, most people have, you'll have heard people say, well, so what? A little bit hotter, we can cope with it. A couple of degrees, it doesn't matter much. Well, I want to tell you that the answer to the question, does it matter, is yes, it does. It matters a lot. It's probably the biggest problem that humanity has ever faced. That's a big claim. It's capable of doing as much damage as a flat-out nuclear holocaust. How can we know this? By looking at the Earth's climate history. That's what we'll do now. This isn't a particularly easy thing to represent on a diagram, but it tells a story without which it's a bit hard to understand exactly the meaning of our present situation. So bear with me a minute, I'll try and explain what this shows. It's a temperature record of the Earth going back the enormous period of 75 million years. This wiggly black line is the temperature record, and when it hits the bottom at the present, it turns red and then jumps up like that. This arrow separates the past from the future. You can see that in the past the numbers represent 20 million years, and in the future they represent 1, 2, 3, 400 years. The red line is actually the IPCC's projection under the circumstances where we don't do very much about keeping CO2 down. Across the bottom is present temperature, and then there's a temperature scale going up the right side. Here is where an asteroid smacked into the Earth and caused an event which extincted the dinosaurs. This one is a thing called the PTM, a sudden warming event which is probably caused by the release of a very large amount of submarine methane. Here is a very significant turn of events. Some cooling event caused the temperature to drop over a boundary and trigger the formation of the first permanent ice sheets in the Antarctic. For 20 million years, the ice sheets behaved dynamically. They shrank and grew depending on variations in the climate and other factors. And then 14 million years ago, they became permanent and began to resemble the ice sheets we know now. 3 million years ago, after another cooling event, ice grew in the northern hemisphere for the first time. The two things I'd like you to take away from this little story are these. Here is a 1 degree boundary between an ice-free northern hemisphere and the northern hemisphere we know. At 3 degrees warmer than the present, an enormously significant boundary appears to exist between an ice-free world and the one we know. In this part, tropical plants grew in Alaska and indeed in Antarctica itself. So this is an entirely different planet, not just a little bit warmer than the world humans have known, but more like the world the dinosaurs knew. Now we're going to just focus down on the last 5 million years here to see a lot more detail. Here it is. This has been reversed. The present is over on the left, the past on the right. This is the era we know as the Pleistocene Ice Ages, 3 million years long, where the climate has this jagged character with many ups and downs. This is the time when humans have existed on Earth, 2 glacial cycles, and this is where the northern ice sheets were born 3 million years ago. The thing to notice about this record is that the jagged character is not an artifact of a rough record, but records true events. For reasons that are not completely understood, the presence of ice in the north acts as a kind of amplifier, and small triggers therefore set off very abrupt and large climate changes. This has been the most important discovery with enormous implications for what's happening in our future. And the last thing is that 1 degree boundary, which is there again. Above that, all the northern ice melts and Earth loses its ice mirror and its northern refrigerator and becomes a completely different planet, with sea level 5 to 10 meters higher. And this is focusing down on the 10,000 years or so, the entire period of human civilized experience. 2004 representing current temperature sticks out a mile. Let me just review this for a minute. First, we know that gas is capable of warming the atmosphere, have been building up very fast for a century or so, and that carbon dioxide in particular is at a concentration in the air now unseen for at least 15 million years. Second thing we know is that Earth is about a degree warmer than it would have been without the human greenhouse effect. The third thing is that another degree of warming would take the Earth into the temperature range where no northern hemisphere ice sheets would survive. We know that another 2 degrees of warming on top of that would bring the Earth into the range of temperatures where even the great Antarctic ice sheet would become unstable. We know that the West Antarctic ice sheet is vulnerable to melting and would probably begin to disintegrate under conditions similar to those which were enough to melt Greenland. We know that another 3 degrees of warming is a virtual certainty if we don't get carbon dioxide emissions under control in the next half century. And finally, we know for a certainty that the effects of an induced climate catastrophe would become unavoidable once they got well underway. They would escalate for a couple of 100 years at least, and they would last in total for many thousands, tens of thousands of years. A catastrophic warming would have a great many effects on the entire ecology of the planet, on human society and on all living species. There's no time to go into any of those now, but I will concentrate on one of them just to give you a feel for the scale of the disaster that we're looking at. This is Greenland, a large island in the Arctic Circle, virtually covered by a single ice sheet. That ice is about 2 kilometers thick in the middle of the island. This is the ice sheet that covered Canada and the northern United States as short a time as 18,000 years ago. It's all gone now, but that too was over 2 kilometers thick when it existed. This is Antarctica. This part, which lies west of the Transantarctic Mountains, is called the West Antarctic Ice Sheet. It has about 10% of the ice there, and studies have shown that its geophysical properties make it much more vulnerable to warming and melting than the much larger eastern ice sheet. Now, all land-based ice is made of water taken from the ocean, so when it melts, the water goes back there. In other words, by measuring the ice volume in an ice sheet, you can tell exactly how much water is going to enter the ocean and how much the sea level will rise. It turns out that the West Antarctic ice sheet is good for about 6.5 meters, and Greenland for about 5. This is a story of what happened to the sea level in the warming following the last glaciation. Here is where it began to warm up 18,000 years ago, and here is the stable 6,000 year period, in fact unusually stable, that humans have been around. Stable sea level is very conducive to civilization because it makes inshore fisheries more productive, and of course it wouldn't otherwise be possible to live or build near the coast. Now, there's a great deal we don't know about the behaviour of the ice sheets under the conditions that might prevail in the future. But when the IPCC came to issue its 2007 report, it included a rather unrealistic estimate of what sea level rise would occur. And as soon as it was published, many knowing scientists were quite concerned that this would look like false reassurance. One of them was an oceanographer named David Archer, and David went to work to try to show that we really have a lot more to worry about than the IPCC published and is commonly understood. I want to show you how he summarized his work in this graph next. This is the way David figured it out. Even if we don't know everything we need to know about the physical behavior of ice sheets under conditions of melting, and even if some ice sheets behave differently from others. There ought to be a kind of relation between the amount of melting and the level of the sea. And so he took 3 or 4 well-known points, stuck them on a graph to see what would happen. Down here is the coldest part with the lowest sea level. Up here is the hottest part with the highest. This point represents where things were at the coldest part of the last ice age. This one here represents the warmest part of the warm period before that, 120,000 years ago. And this one is the point where the original northern ice sheets began to grow. This one at the top is where the Earth was at its warmest 50 million years ago. It's off the straight trend line because, of course, there wasn't any ice there then. And here's the thing. The IPCC forecast for a bit less than 1 metre, about 2 feet or so, of sea level rise for 100 years from now is way off the chart when it ought to be on that line. 2.5 degrees of warming is good for about 35 metres of sea level rise. That's as plain as day. We don't know how long it would take, but we know if we got that warm, sooner or later the sea would rise that much. Well, you don't need a lot of imagination to understand the disaster that 5 or 10, let alone 30 metres of sea level rise would be. Quite apart from displacing billions of people and drowning incalculable assets, the sea would continue to rise for centuries. So no possible adaptive strategy could work, and retreat would be the only option. And while we're coping with that, we would have to deal with fantastic numbers of refugees, diminished food supplies, growing deserts, vast heat waves, shortages of water, giant storms, and a whole lot else. And that's just the human side of the problem. Other species would have to get by as best they could and would probably fare even worse. The result of Copenhagen has given us much to think about. One thing it's made clear, I think, is that the political systems that we rely on now are just not up to the job of taking the decisions and causing the actions that we need. When you think about it, that isn't surprising. Politicians have never before been asked to induce sacrifices for the people who vote for them so that people of the future will benefit. Many people have thought hard about this. How can we make our leaders do what they should do for the sake of our grandkids? Well, I think the answer has 3 parts. First, it's up to us, all the folks in the world who care about this, to make sure that our politicians get it, understand just how bad and how urgent it is, and how utterly irresponsible and immoral it would be for us to neglect our duty towards these kids, consigning them to live in a ruined world. They must be talked out of their present preference for what Jim Hansen calls greenwash. That's the politician's habit of talking a lot about their commitment and doing nothing that inconveniences anybody. Second, we, the people of the world, have to let them know that we demand this. This is a problem that makes the preoccupations of national politics look crazy. It's simply not going to go away if we use the political system the way we usually do. It may well be that individual countries have to work out solutions to suit themselves. But unless we do it as citizens of one planet, there's no way we can do it in time or thoroughly enough. Tell politicians what it is you want to happen. Finally, we must do something about the big gap that exists between what climate scientists know and what everybody else knows. Now, I'm well aware that there are many people in the public discourse who've been throwing into this gap misinformation and propaganda. Without speculating on their reasons, I can tell you that this has become a big problem, magnifying the effect of such a gap and making political action much harder than it might have been. They call standard views on climate things like alarmist. Some of them even say that the community of climate scientists is a big conspiracy designed to spread lies and make money for themselves. Well, if you find that plausible, you're entitled to a view. But if you're just confused, this is my advice. Don't go to Lord Monckton or Ian Plimer or Bob Carter or Bjorn Lomborg to find out about the climate problem. Go to people who work in it every day, who've mastered the details of a complicated area and who know what they're talking about. Get clued up and spread the word. If you want somewhere to start, try this. This is Jim Hanson's book. Jim's the director of the Goddard Centre, knows more about this than almost anyone else on earth, and is a worried grandfather.